with certain coefficients, but they still remain double excitation with respect to this state. So in this space of three states, I can again construct the secular equation for the state interaction method. I include now three states into state interaction, but still I keep two states for state averaging. I optimize the orbitals only for average of these two states. So, but now I solve 3 by 3 secular equation, obtain three energies. I'm interested mostly in these energies. And as you notice, the coupling elements couple only the perfectly spin paired state with OSS state and doubly excited state with OSS state, but not with each other, because from GVB methodology, these two states are decoupled. But for the excited state, coupling with the doubly excited state is very important, and especially important in the situations of symmetry breaking or charge transfer electronic states. To give an example, the application of this methodology to, say, set of charge transfer, set of molecular systems with charge transfer lowest excited state. There we have TCNE, tetracyanoethylene, and some arene molecules such as benzene, toluene, orthoxylene, and naphthalene as electron donor, and this is electron acceptor. So the lowest excited state is charge transfer character. Homo-LUMO transition is charge transfer state in these molecular complexes. For these molecular complexes, the experimental excitation energies are very well known. The geometries of these molecules are also very well known. And these molecules, they prove to be very difficult for the linear response time dependent DFT to produce the correct charge transfer excitation energy. So, however, REKS.
Sorry. Is it because that you include the open shell case, open shell configuration? Charge transfer state is really you move the one electron from one side to the other, right?
Right.
Is that?
Yes. Because both molecules, they are closed shell, and if I transfer one electron from one molecule to another, I create open shell state.
Open shells. So you need to have open shell configuration.
Yeah,
that's why
yes,
you include
exactly.
those in the middle, right?
Open shell configuration has to be present there, and also there will be some important contribution from the doubly excited.
And you got the three eigenvalues, which corresponds to three states, isn't it? Or
right? Yes.
Am I missing something? Because you said the two states here.
Two states. I perform orbital optimization for average of these two states only. But then I solve for three states. The secular problem I solve for three states.
Is it because that there is no coupling between the DES and PPS?
Yes, yeah, exactly. I simply don't want to include this state into orbital optimization because usually it's very high line state, and it may deteriorate the, say, energy of the average state and orbital optimized orbital.
So it's kind of combination. You can add or exclude particular states for the orbital optimizations, right? You optimize the orbitals for two specific states, even though you have a 3 by 3 eigenvalue.
Yeah. I can extend this matrix by including more and more states.
But optimize only particular states.
Yes. But I optimize only for combination of particular states, or average of particular states.
So in this case, in this case, the OSS is important because you are specifically want to study the charge transfer, right?
Exactly. Yes. This state I want to investigate, and this is important that the state is included into the orbital optimization. Yeah.
Okay. So then, depending on the chemical problem, you might need to change how you calculate the schemes, right? Over schemes.
In principle, I can do that, not with this simple method with two electrons in two orbitals, but with the extended active space. Yes, it's possible to include different states into state averaging, and also add or exclude more states to the state interaction.
Yeah, okay. So depending on the situation, depending on chemical problems, you might have a much more adapted or the optimum the optimization scheme, right? So that's
right. Yeah, that's correct. Yes.
So I think somebody needs to spend some time to understand to properly use this. Okay.
Right. But okay, for set of these charge transfer complexes, charge transfer in the excited state, complexes with charge transfer excited state, for which experimental energies are well known, REKS produces very accurate excitation energies on average, mean absolute deviation from the experimental values is very small, on the order of 0.1, 0.2 eV. So Bisrelip, CAN Bisrelip, Becky half and half produces same number. Bisrelip has much lower content of Hartree-Fock exchange, and everybody believes that Hartree-Fock exchange is important for charge transfer, describing charge transfer transitions. But with a very little content of Hartree-Fock exchange, I still can produce reproduce these experimental energies with reasonable accuracy, less than 0.2 eV. Even without Hartree-Fock exchange at all, this accuracy 0.4 eV for the B-lip functional is much better than CAN-Bisrelip produces range separated functional produces within the linear response time dependent DFT.
It's quite unexpected because TDDFT at least can has the open shell configurations in this.
Yes.
How come it is so bad here?
Yes, that's correct. But I believe that Tom Ziegler has demonstrated that it is not really the density functional which is bad for description of charge transfer excitations, but the linear response formalism itself. He demonstrated by designing a methodology, his constricted variational DFT methodology, that if one goes beyond linear response, then one can reproduce more or less accurately the charge transfer excitation energies, even using the LDA density function.
Is that because of the effect of double excitation you include?
It may be effect of both double excitation and also.
What if you don't include double excitation? In your case, the energy will be.
They will be not much different. Double excitations will become important in the next example I will show in the next slide.
Yeah, go ahead.
But in this specific case, this is probably insufficient orbital relaxation, which is responsible within the linear response formalism, which is responsible for poor description of charge transfer states. Because charge transfer, especially long-range charge transfer, is a really dramatic modification of the orbitals. You remove electron from the electron donor and create cation, essentially, at this place, and add electron to electron acceptor and create an ion. And the orbitals, all other orbitals, not HOMO and the LUMO, but all other orbitals, are strongly modified by these electron transfer. And this effect of orbital adjustment of all other orbitals is poorly described within the linear response formalism.
So you blame the orbital optimization more than the other, right?
Yes, yes. I think that Tom Ziegler arrived at a similar conclusion that orbital relaxation is important for description of the charge transfer excited states.
Okay, yeah.
Right, but the doubly excited state becomes important for situations when we, for example, want to describe electron transfer from donor unit. For example, this is a famous Aviran-Ratner molecule, which was proposed long time ago in 70s, back in 70s, TTF, TCNQ, where tetra-thiofulvalene is an electron donor and TCNQ unit is electron acceptor. And in this molecule, depending on the electric field, if I apply electric field across the molecule, driving electron density from donor unit to the acceptor unit, the electron transfer should occur stepwise. First, in the beginning, one electron is transferred from donor to acceptor unit, and this creates an open shell electronic state. And then the second electron from the HOMO of donor is transferred to the LUMO of acceptor, right? So this will be stepwise electron transfer. This should be ideally stepwise electron transfer. However, if one applies standard Kohn-Sham DFT to describing this electron transfer situation in the ground electronic state even, then you will see that electric field drives not electrons one by one, but the whole electron pair in the HOMO will be somehow distorted and transferred. It will slowly proliferate through all these pi bonds to the donor acceptor. The whole electron pair is driven from donor to the acceptor, not electrons one by one. This is a deficiency of standard Kohn-Sham methodology, which does not allow to describe correctly multi-configurational electronic state. But if we transfer one electron from donor to acceptor, we create a multi-configurational state. And this is indeed correctly described by the SSR methodology, where application of the electric field with increasing strength. First, we on the ordinate, I show charge on the tetracyanophulvalene unit. In the beginning, it's electrically neutral. As electric field strength increases, first electron is transferred. So from charge on TTF goes from 0 to 1. And then as it increases further, the second electron is transferred to the acceptor unit. So this is in the ground electronic state. But in the excited electronic state, because if we excite this molecule, photoexcitation already transfers one electron from donor to acceptor unit. Then the electric field will first, say, leave these at more or less electrically neutral, but it's not exactly neutral, but almost electrically neutral. And then suddenly it becomes totally neutral. So first it drives towards more open shell situation in the excited electronic state. Then it becomes closed shell. And intuitively, this is correct because we had in the excited state, although separation between the donor and the acceptor is quite short, and they have some bridging unit here, which enables some overlap between the HOMO and the LUMO. In this case, we will have that only partial charge transfer is present in the excited electronic state. Then as electric field strength increases, it becomes more complete. Then one electron from donor unit is transferred to the acceptor unit, and we have a kind of a neutral state. And then it again, the whole electron pair is transferred from donor to acceptor. So this is kind of back and forth electron transfer between donor and acceptor, which occurs in the excited electronic state. And in the ground electronic state, this is correct stepwise electron transfer. But TD-DFT and Kohn-Sham DFT, they describe continuous transformation of the whole electron pair from, say, closed shell configuration through closed shell configuration to another closed shell configuration. So this is incorrect. This description is incorrect both in the ground state and in the excited electronic state. So that, I mean, the electron transfer in the excited state and in the ground state can be correctly captured by the SSR methodology or state average REKS methodology, but it is not correctly described by the linear response TD-DFT. So, and perhaps the last example which I would like to show in this section is
Mike.
Oi.
Can I have a little small question Let's
Okay.
back to the previous slide. For the second plot.
You mean which slide? This or?
Yeah, this is no. Next.
All right. Yeah.
In the second plot, you showed the x-axis is electric field, right? Field
Yes.
strength.
Right. Yes.
Okay, then the y is the charge. Is charges calculated, or how can we define this? What 0, 0.1, 2, 3, 4, 2.5 or 2 in this?
You mean electric field strength or?
No,
yeah.
charge. You said the
this charge I calculated from molecular populations of atoms on the TTF unit.
Okay. Then it's a function of the electric field, right?
It becomes function of the electric field, yes.
And then electric field is taking the negative value. Is what does
it also includes direction.
Okay.
So I can so zero electric field somewhere. Here I can include say electric field in positive direction or in negative direction. So that's what it shows.
Okay. Thanks. Yeah.
Right, and the last example of let's say application of REKS to some model systems is excitation energies of cyanide dyes. So these are these pi conjugated molecules. The two amino groups can be separated by varying number of double bonds. So the number of double bonds can be 5, 7, 9, 11. So that will be a long chain. And these molecules are regarded as some kind of push-pull molecules because their say closed shell electronic structure corresponds to twitter-ionic configuration with positive charge on one end and neutral other end. So generally these are cationic molecules, of course. And these fluorescent dyes are used often in biotechnology as fluorescent labels. So they have long living excited states and they can fluoresce with varying wavelengths, at varying wavelengths. And depending on the length of the chain, their excitation wavelengths in these molecules changes, and it changes almost linearly with the length of the chain. And as you see here, state average REKS or SSR is in a very good agreement with the diffusion Monte Carlo methodology. So best theoretical vertical transitions for these molecules were obtained using diffusion Monte Carlo again. And REKS is in a very good agreement with DMC, whereas linear response to DDFT provides quite poor description of these excitation energies. And these excitation energies are strongly overestimated. I mean, vertical transitions are strongly overestimated, more than half EV or sometimes 1 EV or more. They are overestimated. And the origin of this overestimation is, again, can be traced back to insufficient orbital relaxation in the excited electronic state, which is inherent in the linear response to DDFT. However, state average REKS, because it's a variational method, provides a better description of the orbital